Okay, let's start this seminar. The speaker is Shu-Heng Shao from Stony Brook University. He'll talk about why the pion decay. Please
All
start
right.
when you're ready.
Okay, thank you very much for the invitation. So this talk will be an iPad talk. So it will be more of the format of a Blackboard talk. And in the same spirit, I hope it can be a little bit more informal. So I really encourage questions from the audience, either from the audience in the seminar room or from the audience on Zoom. So please interrupt me anytime if there's anything unclear. So before we talk about pions and non-invertible symmetries, let me just say that in recent years, there has been a lot of development on generalizing the ordinary global symmetries. And all this development goes under the name of generalized global symmetries. And by now it has become a rather big subject with many different kinds of generalized global symmetries. I would like just to mention two of the development. The first one goes under the name of higher form symmetries. So more specifically, higher form symmetry is labeled by an integer, Q. And a Q-form symmetry is a global symmetry that acts on Q-dimensional objects. So the simplest example is actually nothing fancy, but if you just consider the free Maxwell theory of U1 gauge field, no matter, one gauge field, then the Gauss law operator which is an integral over some two surface, which can be a two sphere in your space of the electric flux, is one such higher form symmetry. In this case, it's called a one form symmetry. And the objects it acts on are the Wilson lines. There has been a lot of developments on higher form symmetries, in particular about their anomalies and how they constrain various strongly coupled gauge theory. This will not be the topic of the talk today. Today, mostly I'll talk about a different kind of generalized symmetries. But there's an interesting interplay between the higher form symmetry and the second kind of symmetry, which goes under the name of a non-invertible symmetry. So roughly speaking, a non-invertible symmetry is a symmetry operator without an inverse. In quantum mechanics, Wigner taught us that every symmetry is implemented by a unitary operator or anti-unitary operator if you consider time reversal symmetry. A unitary operator by definition has an inverse. By inverse, I mean it's an operator such that U times U inverse corresponds to doing nothing. But in quantum field theory, it turns out that this is a little bit too restricted. There are interesting examples, as we will discuss later on, where a symmetry has no inverse. So that means while the symmetry operator, let me call it D, while it commutes with the Hamiltonian, there does not exist an inverse operator such that D times D inverse is 1. Any questions so far up to this? I think so far it's just an introductory phase. I haven't talked about any of the details, but if there's any question, please feel free to.
Oh, very simple question. So you are talking about symmetry. So your symmetry is always a global symmetry or include the local symmetry, local gauge symmetry too?
Yeah, thank you for that question. I should have clarified that in the beginning. So I only want to talk about global symmetries, but I want to but I want to clarify what I mean by global symmetry throughout this talk, and in fact, in this whole program of generalized global symmetries. So global symmetry is a symmetry that acts on the operators and states in your quantum field theory. In contrast, gauge theory does not act on any genuine local operators. Genuine local operators are by definition gauge invariant. Gauge symmetry can be viewed as a redundancy in the description of your theory. Calling it a redundancy doesn't mean that it's not useful. Gauge symmetry is extremely powerful. I mean, it's the fundamental description of the standard model, QED, QCD, etc. But in more general quantum system, it could be that there are several different presentations of the same quantum system. This is commonly known as duality. And this happens a lot in condensed matter physics, where one description involves a gauge field, but in the other description of the same quantum system, there is no gauge field. This, for example, arises in the context of particle-vortex duality in condensed matter physics. Such duality highlights the fact that gauge symmetry is not something intrinsic to the quantum system. It's a very useful description in some weak coupling regime of the system, but it might not be a fundamental concept of the quantum system. So in a sense, gauge symmetry is not a true symmetry. It doesn't act on any state in your Hilbert space. Global symmetries, on the other hand, is an invariant characteristic of your quantum system and should be matched across any duality frame. So in the rest of the talk, I will use the adjective global to mean that it's not a gauge symmetry. Historically, the word global was introduced to mean that the symmetry parameter is a constant in space-time. But that's not going to be the sense that we use the word global here. So it's a rather unfortunate and awkward terminology. But these days, at least in the community of people studying generalized global symmetries, people use the word global to be contrasted with a gauge symmetry.
I have a naive question.
Yes, please.
According to your broad definition of non-invertible symmetry, does supersymmetry count as an example of non-invertible symmetry?
Yeah, that's an excellent question. I thought about it for a little bit, but not in any details. So let me just say that in this talk, I'll try to focus on internal symmetries. Towards the end, I'll say a little bit about time reversal symmetry. Now, supersymmetry or Virasoro symmetries involve space-time translation, rotation, and therefore it's a little bit outside the scope of this talk. But I think the short answer to your question is yes, but in a way we're very used to that.
Okay, great, thanks.
In fact, non-invertible symmetry has a very long history in theoretical physics. When people study integrable systems in the 60s, there are infinitely many higher spin conserved charges that commutes with the Hamiltonian, but they do not lead to any unitary operator. So in a broad sense, they can also be called non-invertible symmetry. But in the rest of my talk, I will primarily focus on internal non-invertible global symmetries.
Okay. Thank you.
Yeah. All right. Okay. All right. So a lot of the development of higher form global symmetry started with a paper by Gaiotto, Kapustin, Seiberg, and Willett around in 2014. On the other hand, the development of non-invertible symmetry has a very, very long history. So I'm going to draw a lot of dots here. In fact, various aspects of such non-invertible symmetry were already kind of known back in 1989 in the context of rational conformal field theory. Of course, it was not called a non-invertible symmetry at that time. Then there were many developments in the middle, in between, but it was around the time of maybe 2017, 2018, people started to put all this non-invertible conserved operator into the framework of generalized global symmetries. Let me not try to give the full references here. You can find them in some of my papers. But the development of the history goes something like this. Let me draw a two-dimensional diagram where the vertical axis stands for the space-time dimensions, D. Sitting at the origin is the ordinary global symmetry. In the terminology of higher form symmetry, when Q equals 0, that corresponds to the ordinary symmetry. So that corresponds to zero form symmetry. And ordinary global symmetries are, of course, invertible. So that's the origin. And then there has been a lot of development since 2014 on the higher form global symmetries. But they are mostly invertible. In D equals to 2, there are many interesting examples of non-invertible symmetries. And they lead to interesting constraints on dynamical systems, etc. But for a while, and let me say, it has a long history, and there has been a lot of development since 2018. But for a long time, this two developments or generalization of global symmetry seems to be orthogonal to each other. There are some non-invertible higher form symmetry, but I'm not going to say too much about them. That was known for a long time. In fact, Icho, my student and collaborator, will talk about one such example in the talk tomorrow. But for a long time, it wasn't clear if there's any non-invertible zero form symmetry in higher than 2 dimensions. And it was until 2021 that people realized a very general way to construct these new symmetries in higher D. And that led to a lot of excitement in the past 2 years with a lot of examples of non-invertible symmetries in realistic quantum field theory. This includes the free Maxwell theory, QED with fermions, QCD, and also in axial physics. So today, I will talk about this part of the story. In particular, I'll focus on the QED and QCD story. But I wanted to give this introductory remark to say that all this development are built on the separate development on higher form symmetry and non-invertible symmetry in 2-dimensional conformal field theory. Okay. So now let me switch gear to start with something that I think everyone should be very familiar with, which is just 3 + 1 dQED. This is the Lagrangian. Yes. This is the Maxwell term plus a single Dirac fermion. So psi is a Dirac fermion, and it has unit gauge charge, and I only have a single species of Dirac fermion. And F mu nu is the exterior, F is the exterior derivative of the U1 dynamical gauge field. All right. This is probably the 4th or 5th Lagrangian anyone has studied when taking a quantum field theory class. And I'm making a minimal assumption here. I just have one species of Dirac fermions with unit U1 gauge charge. It can be generalized, and the symmetries will be even more interesting. Now in QED, there's a classical symmetry, the classical chiral U1 symmetry. Which acts on the Dirac fermion in the following way. It rotates the Dirac fermion with the important gamma 5 matrix up here. That means it rotates the left fermion and the right fermions oppositely. Don't worry too much about the factor of 2 here. I put a factor of 2 just so that alpha is identified with alpha plus 2 pi. You can see that when alpha is 2 pi, this becomes just a minus sign, and that's part of the gauge group. Now, famously, the classical chiral U1 symmetry is anomalous. And that's the famous Adler-Bell-Jackiw anomaly. It says that U1A is not the symmetry quantum mechanically. I'll say a little bit more on exactly in what sense is not a symmetry in the traditional sense. And the history was that at that time, people were confused. So this was in 1969. In 1969, people were confused about the problem of neutral pion decay. They thought neutral pion was the Goldstone boson for the chiral symmetry of the strong interaction, the chiral Lagrangian. However, if the neutral pion were really a Goldstone boson, then it wouldn't have a coupling with the gauge field in the following way, because it violates the ship symmetry of the Goldstone boson. But on the other hand, the experiment observed that the dominant decay channel of the neutral pion is going to 2 photons. And that requires such a turn in the chiral Lagrangian. The resolution by ABJ was that the global symmetry associated with the neutral pion is not really a global symmetry quantum mechanically, it's anomalous. And by matching the anomalous global symmetry transformation, they were able to compute the coupling constant in front of pi 0 FF in the chiral Lagrangian and match with the experiment. So that was a beautiful story at that time. But if you think about it for a little bit, there's something very, very slightly counterintuitive. Typically, we celebrate when we discover a new global symmetry. We use the new global symmetry to do anomaly matching. We use it to derive selection rules, new conservation laws. But in the story of ABJ, it was exactly the opposite. It was the absence of a global symmetries that leads to the quantitative calculation of the coupling constant between pi0 and the photons. So how come we can learn so much from the absence of a global symmetry rather than the presence thereof? And that was one of the motivation for the project that I'm describing to you today. The motivation is to reinterpret the classic results by ABJ, not in terms of the absence of an ordinary global symmetry, but in terms of the presence of a generalized global symmetry. So that's motivation number one. Motivation number two is that when you go around and ask people, is the chiral symmetry a symmetry of the massless QED? You get all kinds of answer. And people even say that the correct answer is that it's both yes and no. And that's really the worst answer you can expect from a yes or no question. People who say no is because there's no conserved current. The conservation equation is anomalous, as I will review later, so there's no global symmetry. On the other hand, people also say, but it's actually a symmetry in flat space-time, even though there's no conserved current. And both answers are correct. In flat space, the anomaly is mediated by the instanton. However, there's no instanton in flat space-time for a abelian gauge group because pi3 of U1 is trivial. So if you're a flat space-time person, which I believe most of us are, and you just gather electrons with positrons all day long, you are never going to see the effect of the ABJ anomaly. In fact, we all know very well a particular consequence of the chiral symmetry, which is that when you scatter electron with positron, the helicity has to be conserved. In the massless QED. But if you look at all the textbooks, no one dares to explain the helicity conservation in terms of the chiral symmetry. Because all the authors knew that down the road, there will be an anomaly for the global symmetry, for the chiral symmetry. So instead, if you open any quantum field theory textbook, such as Peskin and Schroeder, the way they explain the helicity conservation is by the explicit manipulation of the gamma-5 matrix. They move the gamma-5 matrix from one side of the trace to the other side, you get a minus sign, and therefore helicity has to be conserved. But much more highbrow understanding is that there is a chiral symmetry in flat space-time because there's no instanton for a abelian gauge group, and that's the reason why helicity has to be conserved. At this point, you might take the perspective that, okay, so there is a symmetry in flat space-time. That's all we care about. Our real world looks very much like a flat Euclidean space-time. So why bother with all this non-invertible symmetry or generalized global symmetry? That's a perfectly valid point of view until you want to talk about monopoles. Magnetic monopoles, in effect, creates non-trivial topology. And indeed, we learned from the work of Kalin and Rubakov that a non-trivial monopole, in the monopole scattering problem, the helicity is violated. So to have an exact global symmetry when there's a monopole, you really need to go beyond the ordinary chiral symmetry. Just one second. Okay, any question at this point to the introductory remark on ABJ anomaly?
Your motivation one, I mean, is it always possible to read that if there is ABJ anomaly, then you can always reinterpret it as a global, generalized global symmetry? Is it always possible? In any cases?
The answer is no. So it really depends on the details of the anomaly. Sometimes the anomalies leads to a non-invertible symmetry. Some other times it leads to a higher group. Some other times it just leads to nothing. For instance, if you ask this question in the context of eta prime, which comes from which is associated with the chiral symmetry that has an ABJ anomaly with an SU3 gauge group, then there's no generalized global symmetry behind. So it really depends on the detail. If time permits, in the end, I will try to comment on the physical reason behind why sometimes there's a non-invertible symmetry and sometimes there isn't. And that's a great question. Any other question? Okay. If not, let's proceed. So what ABJ taught us back in 1969 is that let's define the axial current in the following way. This is the naive current that you would expect it to be conserved. However, ABJ showed that. So here I'm going to use the differential form notation. I hope that's okay. So I treat JA as a one form, and D star here is the Hodge dual. So D star JA is just a fancy way of writing D mu J mu A. So what ABJ taught us is that D star JA is 1 over A pi square F wedge F. So in component, this means that it means epsilon mu rho sigma, F mu F rho sigma, up to some coefficient. A side comment is that here I normalize my gauge field such that when you integrate F along the two cycles, it's always 2 pi times the integer. In the standard quantum field theory textbook, the normalization differs from here by a factor of E squared. So that's why in quantum field theory textbook, there's typically E squared over here. But here we, in this talk, I choose a different normalization that will be more convenient for later purposes. All right. So this is the anomalous conservation equation. JA is not really conserved. It's violated by F wedge F. So I'm going to start from here and ask myself, is there any way that we can construct a conserved engaged invariant operator? And this was the point that I realized that I forgot to give references. So I apologize for that. So starting from this point, the work is based on a paper I wrote with my student Icho Choi and my longtime collaborator Hota Len from MIT. And there was we wrote this paper in the summer last year, and the archive number is here, 05086. And immediately after our paper, there was another one by Clay Cordova and Kantaro Omori. Both of them are also my longtime collaborator. Here's the archive number. All right, sorry about that. So we're going to take this as given and ask, can we build a conserved quantity? After all, that's what we mean by a symmetry. Okay. So we'll have 3 different trials. So in trial number 1, we're just going to integrate the current directly. So normally, if you have a conserved current, so note that I don't put a superscript A here, it's just an ordinary conserved method current. Then what do? We integrate the time component of the current to get the conserved charge. It is conserved because if you hit it with a derivative, you can bring it inside the integrand and rewrite it using the conservation equation and find out it's a total derivative and therefore that vanishes. Starting from a conserved charge, you can write down a unitary operator, which is e to the I theta q, that implements the u1 rotation by an angle theta. So this is the unitary operator that is conserved. So note that I would like to distinguish the charge from the unitary operator. They differ by exponentiation. But you should be slightly bothered by this expression because we're working in in relativistic quantum field theory. And Einstein taught us that in relativistic quantum field theory, especially when you put it in Euclidean signature, there's no difference between time and space. Time and space are really on the same footing. However, this expression treats time and space very differently. We should look for a more covariant expression. The more covariant expression is to define this object u theta on a general 3-manifold in space-time. Where you integrate star j, which is a 3-form, on a general closed 3-manifold. When the 3-manifold M is the whole space at a given time, this gives you an operator. On the other hand, when M extends in the time direction, this gives you a defect that modifies the quantization of the Hilbert space. It's something that localizes, say, in x equals to 0, but extends in the time direction. Well, the nice thing about working with the relativistic quantum field theory is that both the operator and the defects are capturing a single object that we call u theta of n. All right, any question up to this point? So here we see that the charge is conserved because of the conservation equation. But more generally, you can think about this object u theta of n. And the nice property is that it's topological. It means that it's not only invariant under deformation in time, but also invariant under deformation in space. So you can insert this u theta of m in any Euclidean correlation function, and the answer will depend on m in a topological way. Topological might sound like a very fancy word in physics, but you should really think about topological as a pseudo version for conservation in relativistic quantum field theory. And that is why symmetry and topology has a very close relation. So this is the story for an ordinary global symmetry that's non-anomalous. Namely, you have a one-form current that whose Hodge dual is literally closed. If you have a closed form, then the integral on any closed 3-manifold will be topological by Stokes theorem. But in ABJ, in QED, we don't have that. D star JA is 1 over A pi squared F wedge F. So if you naively define the operator as we just did, let me change it to alpha. This is not conserved, or more generally, not topological. It is gauge invariant for whatever that is worth. So that was the first trial. We start with the anomalous conservation equation, but we didn't get a conserved operator. The second trial, which was done by Adler in 1969 paper, was to consider the following operator. So I call it U hat. Where you shift the integrand by this term. Okay, what is ADA? Actually, let me make it a different color because this term will be important later on. The ADA in component is rho sigma A nu d rho A sigma. So that gives you a, sorry, I don't mean to take this. It's A mu d mu A rho dx mu dx mu dx rho. So that makes up a 3 form. The nice thing about the term in the parentheses is that if you take the exterior derivative in it, it vanishes. This follows from the anomalous conservation equation here. All right, any question up to this point? All right, so far so good. But notice that I put this operator in quotation marks. And the reason is because this operator, while it's formally conserved, but it's not gauge invariant. The reason that it's not gauge invariant is because it involves the explicit gauge fields A here. The dA, of course, is fine. That's the field strength. The field strength in abelian QED is gauge invariant. But it has an A here. So under the gauge transformation of A, the current here is not gauge invariant. So at the end of the day, we don't have a conserved current. You can attempt to shift the naive current by this Chern-Simons term, but the result, which is the term in the parentheses, is not gauge invariant. So it doesn't count. You might be hoping that after doing the integral, this term is gauge invariant. Unfortunately, that's also not true. You might take a step back and hope that maybe you first do the integral and then put it in exponentiation. Does it have a chance to be gauge invariant? And even that is not true. And let me just quote a fact about this. So the fact is that exponential, the integral of in over 4 pi ADA is gauge invariant if and only if n is an integer. Here, there's a minor assumption on the manifold being spin, but let me not worry about that. So I'm not going to prove this fact. This is a well-known fact in Chern-Simons gauge theory, pioneered by the work of Witten in 1987. And here I'm just going to quote the result. If you compare this part and this part, you see that for us, the coefficient n corresponds to alpha over 2 pi. Alpha over 2 pi is not an integer, and therefore this term is never gauge invariant. So we seem to have a dilemma. We either have a conserved but gauge invariant we have a gauge invariant operator that's not conserved, or we have a formally conserved operator but it's not gauge invariant. And that's why I put it in quotation marks. And that was the status back in 69. We just failed to come up with the exact conserved quantity.
Question?
Yes, please.
So could you a bit more explain the gauge invariance of this operator, in particular the exponential a wedge dA, and
Yes.
in this question. So
Yes.
if we consider gauge transformation of A, so
Yes.
we have d lambda wedge dA, right?
Yes, I'm writing it down as you speak.
And then we can use Stokes theorem,
Very good.
and this can be rewritten as the some surface integral, right?
Naively, yes, but there's a mistake there, and let me explain.
Yeah.
That's an excellent question. I was trying to get away from it by quoting some fact, but since you asked, let me get into it. So here I assume M to be a closed 3 manifold. So naively, you would say, oh, under the gauge transformation, you get the total derivative here. I can write this as d alpha dA, so it's a total derivative, and therefore this term seems to match. So I will have a gauge invariant operator.
Yeah.
This is true locally, but not globally. And the point is that alpha, the gauge parameter, as well as the capital A, they are not true functions. They are sections over a bundle. They are not single value functions. For instance, if your spacetime has a circle, then alpha can wind around the space circle. It can have a non-trivial winding number. And it's precisely those large gauge transformation that makes this operator non-invariant. And this is the reason why in the beginning I stressed that I'm talking about QED with U1 gauge group here. If the gauge group is a compact gauge group, then we have to allow gauge transformation that wind. And those large gauge transformation is precisely what makes this operator non-gauge invariant. Only when n is an integer, one can show that this whole thing is gauge invariant.
So if I remember correctly, so people sometimes refer some monopole to discuss the gauge invariance of this operator. Is that correct? Or could you comment on, yes.
It depends on the context of your question. Are you in 2 plus 1D or 3 plus 1D?
Maybe 2 plus 1.
Right. So in 2 plus 1 is a different story. Well, because you see here, M is the support of my operator or defect. I'm not viewing M as a space-time manifold for 2 plus 1D system. So in 2 plus 1D, there's a whole separate discussion on the monopoles in Chern-Simons gauge theory.
Okay.
But it's related, but not directly related. So let me not get into the details of that.
Okay. Thank you.
Yeah, thank you for the question. Any other questions?
Shu-Heng, can I ask a question regarding
yes.
this non-gauge invariant current? So
Yes.
I know this sounds very crazy, but could it be possible to replace this Chern-Simons term by eta invariant?
Eta invariant.
Yeah, to make a gauge invariant? Because I know that the Chern-Simons term is different to eta, but when you take a derivative, they behave very similarly.
You mean the eta invariant of the manifold M?
Yeah, the NMA. Yeah.
Yeah, but wouldn't that be something more gravitational, if I'm not mistaken?
So you're worried about this gravitational terms when you take a derivative? Okay, I
thought
see.
that, yeah. There is a very nice paper by Zhuben Wang and Pavel Putrov, where they take into account of the gravitational anomaly. But I'm not there. Here I'm
not talking about the eta of M only, but I also consider this eta M and A.
Right.
In other words,
they did it all together. The paper by Zhuben and Pavel, they did it all together.
Okay. Sorry, yeah, I know this sounds very crazy, but yeah.
Yeah, I don't know how, yeah. Well, in their paper, I think that's what they did in their paper.
Okay, thank you.
Yeah, sure. But I don't think you can cure it just using the eta invariant. I don't think that will give you something.
I expect so, yeah.
They also add the T2FT,
All right.
as I will do later on. Yes, there was another question.
Yeah, I was just wondering whether you can have a non-trivial winding on a flat space-time for DA without adding anything into space-time, like creating a direct string so that significantly changes the topology of space-time.
Right. So without any monopole, and if you are just in flat space-time, then there's no winding. So if you take M to be R3 here, you can remove the quotation mark. In fact, that's literally what Adler wrote in his 1969 paper. He take M to be R3 and he find the gauge invariant operator. And this is another explicit way to say that chiral symmetry is a symmetry in flat space-time.
I see. Okay, next.
Yeah. So we're not saying, so everything that people said in the past was correct. Here we're merely giving an alternative interpretation that can give you a more coherent answer and leads to further generalization. Any other questions? Okay. So how do we obtain a conserved and gauge invariant operator on any space-time manifold? So that brings us to the recent development from 2022. But to make progress, let's be less ambitious and focus on the case when the chiral rotation angle alpha is 2 pi over n, where n is some random positive integer. It better not be 1. So 2, 3, 17, whatever. And let's take a look at the operator U hat that we just talked about. So give me a moment just to write it down. All right, so I didn't do much. I just substitute alpha equals to 2 pi over n into this expression. I still put that in quotation marks because this is still not gauge invariant. You see, the transaminase term, the red term that's causing us problems, is still not properly quantized. The integer n is in the denominator rather in the numerator. So we didn't solve the problem. But let's take a closer look into this term. Oops, I'm sorry, I missed a factor of I. Okay. If you just look at this term in isolation, so let me actually draw a line between here and there, because we're taking a slight detour that I promise will be rewarding in a few minutes. If you look at this term in isolation, it actually makes a prominent appearance in a completely different physical setup. And that is in the context of the fractional quantum Hall effect. This red action is commonly used as the response action for fractional quantum Hall effects with filling fraction 1 over n. In that context, M is the space-time manifold of your tabletop experiment for the fractional quantum Hall effects. The fractional quantum Hall effect is the spatial dimension is 2. and you set up a large magnetic field in your system, and that magnetic field is associated with this gauge field. So A in that context is a background U1 gauge field, which gives you the magnetic field that you tune in your lab. And M there is the 2 + 1D space-time. And this is the reason I'm drawing a line between here and here. Up here, M is the support of an operator in the 3 + 1D QED. Capital A there is the dynamical U1 gauge field. It's the field that gives you the photon. Down here, we're talking about the 2 + 1D fractional quantum Hall effect. M is the full total space-time of your 2 + 1D system, and A is a background U1 gauge field. It's not dynamical, it's background. You have some large magnetic field that's fixed. But now you might wonder, how is it possible that our condensed matter physics friends are using a gauge non-invariant action to describe a realistic tabletop experiment? Well, the answer is that the red action is actually not the precise gauge invariant action. It's correct locally, but not correct globally. Globally, there's a different action, which I'm going to write down right now. Of the following form. The blue action has two gauge fields, little a and capital A. Capital A is the background field. Little a, on the other hand, is a dynamical field. It sometimes goes under the name of statistical gauge field. The blue action is perfectly gauge invariant because you see both Chern-Simons terms are properly quantized. It's an integer over 4 pi in both cases. So this one is gauge invariant, this one is not. Formally, you might want to relate them by integrate out little a to obtain A equals minus capital A over M. If you naively substitute this in here, you retrieve the red action. But that's not legal because both little a and capital A are properly quantized. What do I mean by properly quantized? I mean the integral of their magnetic fluxes are 2 pi times the integers. And therefore, you cannot divide a properly quantized gauge field by an arbitrary integer and set it to be another properly quantized gauge field. Indeed, you don't expect them to be really equivalent. You cannot perform a legal manipulation to relate the legal action to an illegal one. At the end of the day, in the context of fractional quantum Hall effects, the blue action is the more precise and gauge invariant expression. Any question at this point? All right. So motivated by this, well, we're coming back to QED. So return to QED. Motivated by this discussion, it's clear what we should do next. We should just replace this problematic red term in this operator of QED by the blue one. In this way, we define a new operator D that's labeled by a positive integer in the following way. All right, let's unpack this expression. So in this term, we basically replace the red term by the blue term. But then you should ask, what's the meaning of this little a gauge field in QED? And that's the reason why we include this path integral over little a. This little a should be thought of as an auxiliary one-form gauge field that only lives on the support of this manifold M. It's like a dummy variable, if you wish. Little a is completely confined to M. It doesn't propagate in the bulk. Little a doesn't give you any asymptotic states in QED. In the
one
bulk,
question.
yes, please.
Yeah. So you don't include the kinetic term for A?
I don't.
Okay.
I don't. Very good.
Mm.
And the reason I don't is because a kinetic term for little a will have a scale, right? When you write down a Maxwell term, a Maxwell kinetic term for a gauge field in 2+1D, recall that little a only lives on 2+1D. If you write down a Maxwell 2+1D Maxwell term, the electric coupling has mass dimension. And therefore, it's not the topological operator. And therefore, it's not the conserved operator. The goal here is to construct a conserved operator. So I better not.
Yeah, right. Thank you.
Yeah, thank you. So in the bulk QED, I didn't change anything. I still have the Hilbert space with photon state, with the positron state, with the electron state. This little a is like an impurity that the condensed matter physicists study. It's completely localized in in a higher codimensional manifold in space-time. So this is probably the most important equation in this talk. What are its properties? It's gauge invariant, first of all, because all the Chern-Simons terms are properly quantized. It's also conserved. This fact is slightly more non-trivial. One intuitive way to understand it is because here we put a fractional quantum Hall state. A fractional quantum Hall state is described by a TQFT, a topological quantum field theory. And because it's topological, it in particular implies it's conserved. The argument is not completely correct because one might be worried that the coupling between the TQFT and the dynamical QED gauge field might break the topological nature. But that actually doesn't happen. And that was shown rigorously in our paper using the technique of higher form symmetry. It's a technique we call half gauging the higher form symmetry. But let me not talk too much into that. That really requires some heavy machinery into higher form global symmetry. But if you are curious, you can look at our paper for a detailed proof. At the heuristic level, you can think about it, think about the topological nature that follows from the fact that we are coupling a TQFT to the chiral rotation. Okay, so it seems to be all good news at this point. And at the level of the slogan, you can say the following. You can say that the fractional quantum Hall state cures the ABJ anomaly. We find a gauge invariant and conserved quantity in QED. But there's no free lunch in theoretical physics. There is a price we pay. And the price we pay is that D is non-invertible. In particular, it's not unitary. Unitary operators are always invertible. How do you check if an operator is unitary or not? That's very easy. You just multiply D with its own dagger. As we do that, it's important that we have an auxiliary little a gauge field for both D and D dagger. So we have to write that twice. We have dA. We also have dA bar. Let me say that bar is just part of the name. A bar is the real auxiliary gauge field for D dagger. And the rest is easy. We just add up this term from D and a similar term from D dagger. So the JA part will cancel, but these two parts add up. So this is probably the most complicated equation in the talk, but don't worry too much about it. Most of the details won't matter. All right. So d times d dagger is something complicated. It's a mouthful. It includes two auxiliary integral, a bunch of Chern-Simons terms. Now, you don't have to worry too much about what this operator is. This operator has a name. It's called a condensation operator. It started its life in condensed matter physics, but has recently propagated into the high energy physics community as well. If you're curious about what this is, I recommend another paper that we wrote, that I wrote with Rupantakis, Sahan Safnashri, and myself in 2022 for this operator. All you need to know about this operator C today is that it's not 1. Therefore, d times d dagger is not 1. And that's why d is not a unitary operator. Let me say briefly how you should think about this C operator. It's an oops, I noticed that I forgot the integral. It's an operator that's supported on a 3 manifold. Little a and little a bar are dummy variables. They are going to be integrated out at the end of the day. The capital A is the magnetic field. So looking at it very superficially, you are basically trying to define a magnetic flux through some 3 manifold. That sounds weird. How do you define a magnetic flux in the real world? You choose a 2-sphere, and you measure the magnetic flux coming out of the 2-sphere. You don't choose a 3 manifold. Magnetic flux is conventionally defined on a 2 manifold. So this object is trying its very best to be a magnetic flux operator through a 3 manifold. And that's basically the essence of condensation operator. And surprisingly, this can actually be done in a Lorentz invariant way. And the trick is to introduce this auxiliary gauge field. Anyways, all you have to know about C is that it's some kind of magnetic flux operator, but it's not the identity operator. So this is in what sense we call D a non-invertible operator. It doesn't have an inverse. The closest thing you can have is to multiply D with D dagger and get this C operator. Any question about this new operator D?
So I have a question.
Please.
So in this expression, so A and A dagger, so they are completely independent.
Right.
And then, so I think, so naively we can perform the integration respectively. And after that, so we have Chern-Simon Lagrangian, right? For each A and A dagger.
So you cannot really integrate out little a. You can do it locally, but globally you cannot because of this non-trivial action.
Okay. Sorry, could you go back? Could you go back the slide?
Yeah. Oh, you mean back here?
Yes. So you introduced yes, you or maybe one more. So you introduced a small a to rewrite the Chern-Simon term in the gauge invariant way.
Yes.
Right?
Yes.
So at least locally, so we can perform the integration.
That's right.
But you are saying that globally, so so they are not, I mean, the integration of A and A bar, so they are not equivalent. That's what you are saying?
I'm saying that the red action and the blue action are locally equivalent, but they are not globally equivalent. In fact, the red action is not even globally well defined because it's not gauge invariant. So globally precise gauge invariant action is the blue one. And that's why I always keep globally ill-defined action in quotation marks.
Okay. So that's why you said, so we cannot perform the integration, the path integral, so globally.
Correct.
And as a result, so you have no invertible property. So,
that's correct. That's correct. Yes.
Okay. Thank you.
Yeah, thank you. Any other questions?
Shu-Heng, what is the dynamical reason to have this small a field on every 3 manifold?
The reason is because without this dynamical gauge field, I cannot write down.
I know. Yeah, I know the reason why you want to introduce A, but forget about this construction and think about 4D QED, and with coupled to massless Dirac fermions, then you are saying that on every 3 manifold we need to have this dynamical emergent gauge field supported on this 3 manifold.
Suppose I want to insert my new operator D along a given 3 manifold, then I have to introduce a dynamical little a gauge field on that 3 to even define this new operator D. It doesn't exist in every 3 manifold. It only exists in those 3 manifolds where you insert an operator D.
Oh, I see.
It's like an impurity.
I see. Now I understand. So you want to define this kind of operators. Fine. Okay.
Yeah, this A is contained in the very definition.
Definitions of operators. Okay.
That's right.
Okay. Thank you.
Yeah. Another way to see that it's non-invertible is that exponential is invertible, but our operator D is a path integral of exponential, and that is non-invertible. Unitary, if you just consider sum of unitaries, that's not going to be unitary, let alone a path integral of unitaries. And what is doing that path integral is the little a gauge field. Any other questions?
Sorry, one more. So
yes, please.
If there is no magnetic field, I mean, if dA equals 0, so do you have 1 in the right-hand side?
If there's no magnetic, sorry, maybe can you say again? I didn't quite.
If there is no magnetic field, so the right-hand side is 1.
Right-hand side of which equation? Sorry,
I
you
think
mean
C.
here?
They say C.
Oh,
D
C.
dagger.
Oh,
Yeah, D
okay.
dagger.
Yeah. That's not. It's not a completely meaningful statement to make because capital A is a dynamical field in QED, right? So we should allow all possible gauge field variation in QED.
So,
of course, you can ask the question in the following way. You can say that, oh, let's view the gauge field as a background gauge field, and then we can consider a background configuration of capital A, and then you are right. In that limit, when D capital A is 0, then this is decoupled transassignment theory.
Sorry, I misunderstood. Okay, so A is now dynamical. It's not a background.
That's right. So that's why I drew a line between here and here.
Okay.
In the QED story, capital A is a dynamical gauge field. It's a dynamical gauge field that gives you the photon. It's the reason that we can see each other. But below the line, capital A is a background gauge field, responsible for magnetic field in fractional quantum Hall effect.
Okay. Thanks.
Yeah, of course. Any other questions?
There is no kind of special choice of any parameters to see that C becomes 1. Any special, some kind of condition is there?
There may or may not be. It certainly depends on the manifold M. It certainly also depends on the state you want to act on. But the statement is that it's generally not the identity operator.
I see.
Any other questions? Okay. Now let me make a quick comment that it's very easy to generalize the story to any rational rotation. So previously we did the case of 2 pi over n, but you can do the more general case of 2 pi p over n, where p and n are co-prime integers. And the trick is to use a different fractional quantum Hall state. Or you can think about it as some kind of Zn minimal TQFT. Let me not get into the details of that, but at the end of the day, you again obtain a conserved engaging invariant operator. So the upshot of the discussion so far is that the classical U1A symmetry is not completely broken. Let me write it. U1A is not entirely broken by the ABJ anomaly. Rather, it's resurrected as a non-invertible symmetry. D P over N labeled by the rational numbers. So it's a very weird symmetry. It's a symmetry labeled by the rational numbers. It's a discrete symmetry. However, the rationals are dense in U1. So it's almost as if it's a continuous symmetry, but not quite. Now, looking back at history, it's kind of interesting. So ABJ was in 1969. Before 1969, people thought U1A is a symmetry. After 1969, people thought U1A is not a symmetry. Perhaps a symmetry in flat space-time, but not in general. And the development from last year is that it's actually a non-invertible symmetry. You could have asked, is it possible that ABJ might have thought about these non-invertible symmetries back in 1969? And the answer is no. It's impossible that ABJ came up with this construction. And the reason is because the fractional quantum Hall state was not discovered until 1982. In fact, even the Chern-Simons term was not discovered until the 70s. All right. So now let's take a closer look into what this non-invertible symmetry. This non-invertible symmetry acts on the Dirac fermions as an invertible chiral rotation. The reason is because all this coupling to the capital A gauge field, all this little a, they are not the Dirac field is not sensitive to that. This can be better understood in terms of higher form symmetry, but let me not give that explanation. The upshot is that as far as the Dirac fermion is concerned, this non-invertible symmetry is actually invertible. It's just doing the invertible chiral rotation on the Dirac fermion. And this gives an exact reason why helicity is conserved in QED. Now you don't have to apologize for being in flat space-time, for ignoring the monopoles, etc. It's an exact conservation law. But as emphasized above, the symmetry D is non-invertible. It's not a conventional symmetry. So it has to act funny, in a funny way, on certain objects in your quantum field theory. So what are those things? It turns out that the non-invertible nature is only revealed when you consider monopoles. So the process you can think about is the following. This is our non-invertible operator or defect. And you can prepare a 't-Hooft line over here. The 't-Hooft line is the word line of a very heavy monopole. It's not dynamical, but it's a line defect. The operator D is topological, so I can freely move this defect around. I can move it continuously so that at some point it goes to the other side of the 't-Hooft line. And after that happens, what you obtain is the following. You no longer just get a line defect. You get a line defect that's, well, you get a disk operator. And this should be thought of. This takes the following form. So what is this operator? The boundary of the disk is the circle right here. So this term is trying to be the integral of A. So it's trying to be, multiplied by the H. So this blue piece is trying to be a Wilson line of fractional charge. So the composite object is a dion. It's a dion of electric charge P over N and magnetic charge 1. You start with a monopole with no electric charge, with 1 unit of monopole charge, magnetic charge. After it goes through the non-invertible defect, it's no longer a genuine line operator. It becomes a surface operator. And it can be thought of as a dion carrying a fractional charge. And some of you might have already recognized this. This is nothing but the Witten effect. As the 't-Hooft line goes through the non-invertible defect, the theta angle is shifted. And that's why the monopole turns into a dion. Okay. For those of you who are familiar with the Ising model, this picture should be compared with the non-invertible symmetries in the 2D Ising model. In that case, the non-invertible symmetry is generated by a line operator. The analog of the 't-Hooft line or monopole is an older operator, sigma. And as it goes through the non-invertible defect, it becomes a non-local operator attached to the end of the Z2 line. And that is nothing but a disorder operator. This is a hallmark of non-invertible symmetry. It exchanges order with disorder. It exchanges monopole with dion. Okay. So in the remaining 10 minutes, let me finally get to the story of QCD and pions. So let me phrase the puzzle, the U1 problem, in the modern QCD language. Consider the real-world QCD below the electroweak scale. So the SU2 times U1 gauge symmetry is now broken down to U1 electromagnetic. I'm going to focus on the U and D quarks. I'm going to work in the massless limit. The QCD Lagrangian in this limit has a chiral symmetry, which let me denote by U1A3. So we rotate U and D by e to the I alpha gamma 5 sigma 3 UD. So the 3 here stands for the fact that there's a sigma 3 over here. And the reason for choosing the sigma 3 is because this U1A3 classical global symmetry suffers a triangle anomaly with U1E and M. If you remove the sigma 3, then the symmetry will have a ABJ anomaly with the SU3 color symmetry. But our construction doesn't work for SUN gauge group. One way to understand it is because there's no fractional quantum Hall state for SUN, but there's one for U1. Okay, so now that we have a, and by the way, this U1A3 is exactly the symmetry that's associated with neutral pion. And you shift neutral pion by, it shifts the neutral pion, where F pi is the pion constant, decay constant. Okay. Now, since it has the exact same kind of ABJ anomaly as in QED, the same construction gives us infinitely many non-invertible symmetry in QCD for the real world in the massless limit. But now one should ask, how is this non-invertible symmetry matched by the chiral Lagrangian? The relevant terms for us in the chiral Lagrangians are the pion terms plus the pi 0 F wedge F term. Here, I leave a general coupling constant G here. At this point, for all we know, it could be 0. Here, I normalize my pion field such that it's a compact scalar field with 2 pi F pi periodicity, and F pi is roughly 92.4 MeV. Okay. So how does this chiral Lagrangian capture the non-invertible symmetry? Now, there's a very nice calculation you can do. You basically insert this operator D. In fact, let me just focus on the case when P is 1. You just insert this D as a defect at x equals to 0. Okay. So what do we have? We have a defect at x equals to 0. That's our d1 over n. And what are the terms up here? It's 2 pi I over n star JA3 plus in 4 pi ADA plus I over 2 pi ADA. On one side, we have d pi 0 which star d pi 0 plus IG pi 0 F wedge F, and similarly here. So this is our system. In the bulk, you have the chiral Lagrangian, and on the defect, you have, we make this insertion. In the following, I'm not going to do anything fancy. I'm just going to write down the equation of motion for the field. The equation of motion will have a bulk contribution and have a boundary contribution. We're only going to care about the boundary contribution. The equation of motion for pi 0 give you the following. The equation of motion for little a give you this. the equation of motion for capital A, give you this. And if you stare at these three equations for a little bit, we will see that they are only consistent if the coupling constant G takes a very particular value. And that's indeed the correct value that gives you the experimentally observed pion decay. So in this sense, you can say that this pi0 FF term is really necessary there in the chiral Lagrangian to match the non-invertible global symmetry in QTD. So the neutral pion decays because of the non-invertible global symmetry. This is an alternative interpretation for the pion decay, where that's understood in terms of the presence of a generalized global symmetry, rather than the absence of an ordinary invertible global symmetry. Okay, maybe let me take some question, and if time permits, I can spend 5 minutes talking about the time reversal symmetry. But is there any question up to this point?
Okay, so if you are going to change your topic to time reversal symmetry, let me ask one question about neutral pion decay.
Yeah.
I mean, so in your calculation, you consider only up quark and down quark. So two flavor QCD, right?
Right, correct.
On the other hand, there's a first derivation of pi0 decay by Vess-Jimino, using the Vess-Jimino anomaly, or Witten's interpretation of that is based on SU3 flavor, including the strange quark.
Right.
You know, this
Yes.
topological interpretation of Edward Witten is
Yes.
based on, yeah, right. So
The current
SU3 is crucial. Yeah,
Yes.
right. So but in your case, you don't need strange quark, right?
No.
No. So I think this is very interesting because in the traditional calculation of Vess-Jimino anomaly, you really need three flavors. And then the pi0 2 gamma decay is a kind of consequence of the three flavor chiral symmetry. Maybe my understanding maybe not right, but that was my.
I think what you said is perfectly correct. That's indeed
Yes.
how Witten's current algebra paper was written. But
Right.
With paper, ABJ they already reproduced the pi0 FF term
Yes.
without all the strange quark.
Yeah, that's true. But the pi0, I mean, in order to interpret pi0 as a Goldstone version of the QCD, you also have to include pi plus, pi minus, etc., other pions, right?
Correct.
And then this whole framework really needs that you have to consider SU2 cross SU2 chiral symmetry, or SU3 cross SU3 chiral symmetry. But the triangle diagram for pi0 2 gamma decay need only up and down quark. You don't need a strange quark.
That's right.
So I think that there was some gap between this Feynman diagram calculation and the argument based on topology or consistency of the global current algebra of original Vess and Jimino. So I think it was a puzzle for me for a long time, but I think your approach is at least a kind of a partial answer to my puzzle, I think.
Yeah, we
but do you have a better understanding why you don't need I mean, better understanding about this topological argument based on SU3, not on SU2?
We thought a little bit about how to generalize the story.
Yes, yes.
To mimic Witten's current algebra construction.
Yes,
But we didn't make much progress. The symmetry structure
Mhm.
will be much more complicated because
Right.
the other flavor symmetries. So
Mhm.
we didn't, but there should be a story there. Yeah, so we haven't really worked it out. Here we
Okay.
laser focus on the SU2 part, in fact, just the pi zero part. But you're absolutely right that one can include a strange quark, take the massless limit, then you have a much bigger flavor symmetry, and the whole symmetry fixed in a very complicated way. In fact, there was a recent paper by Zohar Komagolsky and collaborators where they worked the higher symmetry structure just for multi-flavor QED. So you have pieces of Dirac fermion, and that is already complex. And indeed, I think a natural next step would be to consider, say, the 3 quark.
I see.
Yeah.
And in the beginning, you mentioned that your current argument does not apply to eta prime to 2 photons.
Right.
Okay.
That's right. And one way to say it, as I commented earlier, is that here the trick was to use a fractional quantum Hall state.
Right.
Now, there's no fractional quantum Hall state for SUN. So our construction doesn't apply. It's a more invariant way to say it in terms of higher form symmetry, but let me not say that.
Okay, thank you very much.
Yeah, thank you. Thank you for the interesting questions. Okay, I'm basically running out of time, so let me just say in words that in free Maxwell theory, there are also non-invertible symmetries. In fact, the non-invertible symmetry in free Maxwell was first discovered by Icho, myself, and a bunch of collaborators, and then we realized that there's a non-invertible symmetries in QED with Dirac fermion. But the non-invertible symmetry I want to mention in the last sentence or two is the time reversal symmetry. So usually we say in free gauge theory, if you have a theta angle that's 2 pi periodic, then you only have T, have the time reversal symmetry at theta equals to 0 or pi. What we found in free Maxwell is that there are actually more general time reversal symmetry. So there is a non-invertible time reversal symmetry at theta equals to pi p over n for all co-prime pairs of P and N. So this is based on a paper that I wrote with Icho, Hota, right after our Pion paper. And in particular, you can take P to be 1, N to be very large. So it means that on the theta angle circle of the free Maxwell theory, now at these 2 points, 0 and pi, you have the invertible time reversal symmetry. But then everywhere else, you actually have a non-invertible time reversal symmetry that's dense on full time theta angle. Of course, this doesn't solve the strong CP problem. The strong CP problem concerns the SU3 theta angle, which, as I said, we have nothing intelligent to say. But the U1 theta angle could also be a source of CP violation. Currently, we don't have any way of measuring the U1 theta angle because we haven't found the monopole yet. But the message from our paper is that even if there were a non-trivial U1 theta angle, there are still infinitely many non-invertible time reversal symmetry near any value of the theta angle. And in that sense, you have to approximate CP symmetry as far as the U1 theta angle is concerned. So we don't have any, we didn't make any progress towards the strong CP problem. in a way, we only address why the U1 theta angle should not bother us too much. But more generally, I think it's an interesting direction to pursue. Now that we have all kinds of new non-invertible symmetries or higher form symmetry, higher group symmetries in realistic quantum field theory, such as QED, QCD, and axions, as Isho will talk about tomorrow, we relatedly will have new notions of technical naturalness. And is there an opportunity? Is this an opportunity for us to solve some hierarchy problems? I don't know, but I think it's worth exploring. All right, I'll stop here and thank you everyone for the very nice questions. Thank you.
Thank you very much for the nice talk. Any question?
Can I ask you another question regarding this non-invertible time reversal symmetry at theta equal to pi over p over n? So do we still have this non-invertible time reversal symmetry when we have a massive Dirac fermions coupled to background U1?
Yes, very good question. And the answer is yes.
Yes? Oh,
Yes.
I see.
Yes.
So in the case of topological insulators, when theta equal to given by pi, we know that it will give us gap phase, but not trivial, but non-trivial gap phase, which is topological insulators. Do you expect that this theta, when theta equals to pi over p over n, does it give us another type of topological insulator, or?
We have a comment on exactly this point in this paper. And I have to remind myself, and if I say anything incorrect, Isho should also correct me.
Right.
But there were actually already such proposals in the condensed matter physics literature.
Oh.
And the trick is basically the same, that you introduce a fractional quantum Hall state. But yeah, but if I remember correctly, then you will make the phase non-invertible.
I see. It's interesting.
Yeah. So, you know, we thought about this time reversal symmetry first, and then we thought, oh, yeah, maybe we can apply it to topological insulator.
I see.
But then we Googled, there are fractional topological insulators discussed in the literature.
Oh, I see. I didn't know that. Okay. Thanks a lot.
Yeah. Well, yeah.
Another question? I have one very nice question. So in this case, still the time reversal is the Z2, not Zn or something, right?
Well, it's non-invertible. So what I precisely mean by that, there's an anti-linear operator. It's not anti-unitary because unitary means that it's invertible. It's anti-linear operator that commutes with the Hamiltonian. But if you take that operator and multiply it with its dagger, it doesn't equals to 1. It equals to C, the condensation operator. So let me just write it down. It's something like this: T times T dagger equals C. So usually you can consider T, and T squared might be 1, T squared might be minus 1 to the F. But in both cases, T times T dagger is 1. For us, T times T dagger is C. You can ask me what is T squared? Well, that's not super interesting because you can compose my T with another internal symmetry and modify the result on the right-hand side. The interesting point is that T times T dagger is not 1.
Another question? If not, let's thank speaker again. Thank you very much.
Thank you. Thank you for all the interesting questions.
Yeah, thank you very much.
Thank you.
Thank you.
Thanks a lot.
Hello, MJ. Yeah, thank you. Thanks for the night.
Yeah, it was very nice stuff.
Thanks. Okay.
Bye
so
bye.
I guess I'll see you tomorrow.
Yeah, see you tomorrow.
All right, see you. Bye.
Bye.